All right, so this is day 3 of chapter 4, and we're talking about electronegativity and polar bonds. So we're going to talk about what electronegativity is, and then look at how to find that in ALEX, and then we're going to predict if a bond is polar, and then look at, so it's different, a bond can be polar or the molecule can be polar, but if a bond is polar, that doesn't necessarily mean that the molecule is polar. So we're going to look at those two different things. Okay, so the electronegativity value is a numerical rating of how strong an atom can pull electrons in a bond. So if we look at this periodic table, we can see things over here closer to fluorine are going to have a greater electronegativity. They're going to be able to pull electrons towards themselves in a bond more. So the general trend is as we go up towards fluorine, we're going to have a greater electronegativity. So these are some trends that we notice. Fluorine has the highest electronegativity of any element. It usually increases as you go up and to the right. Noble gases are normally not assigned an electronegativity because they don't form bonds. So this is how strong an atom can pull electrons in a bond. Okay, if it's not in a bond, then you can't rate its electronegativity. Okay, so there's an ALEX topic that we're just going to do in ALEX, and we're ordering the elements depending on their electronegativity. So this is in chapter 4. So we can make sure we're in chapter 4. Chapter 4 has 12 topics. So we're looking at predicting the relative electronegativities of atoms. So if we do this, what we're doing is we're just ordering these. So if we look at these elements on our ALEX periodic table, you should always use the ALEX one. Sometimes the periodic tables list these slightly differently because it's like a rating, it's not like a measurement. So if we look at silicon, we can just click on that and we can look at the number. So that's 1.9. If we look at carbon, that's 2.6. And we have oxygen, which is 3.4. So we're looking at decreasing electronegativity. That means we need to start with the biggest one. So oxygen has the biggest one. Oops, that's a 0. Oxygen, and we have to be really careful because ALEX is really picky. We have to make sure that we put the correct element, we spell it correctly, we capitalize it correctly, and then silicon. The next one is oxygen, sulfur, and tellurium. Oxygen, sulfur, and tellurium. And this one follows the trend. We can look. Oxygen is the greatest, then sulfur, then tellurium, 2.1. So electronegativity is always going to be given to you on the test. You don't have to memorize it. You do need to know how to look it up. So oxygen is the greatest, sulfur, and then tellurium in this list. I don't think this will change, but just be careful. Get in the habit of making sure that you're checking the words. This says decreasing, so we start with the biggest, go to the smallest. So this would be a good one to practice in ALEX. It's not that hard. You just need to make sure that you're really careful. Like all of the topics in ALEX, just be careful, pay attention. Okay, oxygen, boron, carbon, decreasing. So oxygen is the greatest, then carbon, then boron. And we can just check that. Let's see, carbon, then boron. Okay. And then the next group is iodine, fluorine, and bromine. And we know fluorine is the greatest. It has a rating of an electronegativity of 4, fluorine. And then this also follows our trend of, as we go down, it's less electronegative. Okay. So that one's not too bad. Just make sure that you're paying attention and being careful. Okay, so now we're going to look at polar bonds. So when the atoms with a different electronegativities form a bond, the electrons are shared unequally. Generally, the difference between electronegativity must be bigger than 0.4 to be a polar bond. So that's what we're going to look for. If the electronegativity is less than or equal to 0.4, then we're going to say that's a non-polar bond. So this is the chart from Alex, and it's giving you some examples. So let's look at these. So we're going to look at chlorine and carbon. So we go to our Alex periodic table. And we're going to look at chlorine, which has an electronegativity of 3.2. And carbon has an electronegativity of 2.6. Let's see. So some of you can probably do that in your head. I'm not going to do it in my head. So 3.2. We're finding the difference. 3.2 and was it 2.6? The difference is 0.6. Okay, so then we decide, is that bigger than 0.4? Okay, yes, that's bigger than 0.4. So, oh, and I've deleted all of the circles. I'm looking at this bond here. This bond between chlorine and carbon would be polar. Let's find a text box. So this would be polar. One would be polar. And which element is more electronegative? Well, chlorine is. Chlorine is the larger electronegativity. Okay, I deleted my elements. So let's look at hydrogen and carbon, 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 oxygen. Okay, I guess let's just look at this. So here we can look at the electronegativity of hydrogen and carbon. The difference between those is 0.4. So then because it's 0.4, if it's equal to or less than 1, that's going to be non-polar bond. Okay, that's what our class is going to cut it off at. We can look at oxygen, carbon. Oxygen is 3.4. Carbon is 2.6. 3.4 minus 2.6. Is that bigger than 0.4? Yes, so that would be polar. So carbon to oxygen is polar. Carbon to carbon, that's the same element. That would be 0, so that's nonpolar. Hydrogen to hydrogen bond would be nonpolar. The difference would be 0. Okay, so we're going to skip. This is some more examples if you want to practice that. There's also a topic in Alex that you can practice doing that. Okay, polar molecules. So what we're looking at in a polar molecule is that the electron density, the electrons are distributed unevenly around a molecule. So water, hopefully if you took biology, you talked about water being a polar molecule. That's really important. Our electrons are going to be pulled toward oxygen because oxygen pulls electrons in bonds. It has greater electronegativity. And hydrogens are less electronegative. So because the whole molecule overall is uneven, we can say, oh, this side is negative, this side is positive, because our electrons are pulled towards the oxygen. Then this is going to be a polar molecule. It also has polar bonds. So the bonds here would be polar. So the first thing we're going to look for is, does it have polar bonds? Then we're going to look at if it's uneven, like it's lopsided. The molecule is not symmetrical. So one side looks different than the other side. I can say, oh yeah, this side is negative, this side is positive, this side has oxygen, this side has hydrogen. It's not symmetrical. Nonpolar molecules have electronegativity that's distributed evenly around the molecule. So if we look at the bond between fluorine and boron here, then our electrons are going to be pulled towards fluorine. Our difference is really different too. So this is our electrons are being pulled towards fluorine, but because we have these counterbalancing bonds, overall there's not one side we can say is symmetrical, or one side is negative and one side is positive. So it's really symmetrical. This is not a polar molecule. So these are the questions that I ask myself. So I look, is there polar bonds? And then what is the molecular shape? And if there are polar bonds, do they cancel out? So that's looking at symmetry. So this one, we can say, like, if we're doing vector addition from our physics class, so this arrow goes up, these two arrows point down and away, so all of our arrows are canceling out. This would be symmetrical. It would be nonpolar. So let's just walk through examples. This one comes up on the test, and it's come up in the homework also. This one is kind of weird. So we have HCN, we have a polar bond, we have two, let's see, this one is the not polar bond. Actually, they're both, are they? Okay, this one's a polar bond. This one's a little bit, this one's an electronegativity of 0.5. Even if these were not polar, we were looking at the electrons are being distributed unevenly. So nitrogen is going to have different number of electrons than hydrogen. This is going to be polar. The other thing we can look at is the electrons are all going towards this nitrogen. These hydrogens are going to be pulled towards the carbon electrons. The electrons on carbon are going to be pulled towards nitrogen. So nitrogen would be our most electronegative element, and this would be a polar molecule. Okay, the next example is CH4. This is going to be a nonpolar molecule. This molecule, we have carbon with 4 electron groups around it. This is going to be tetrahedral. Anytime we have a tetrahedral molecule and all of the groups are identical, that's going to be nonpolar. Anytime we add anything else, so if we have one different group, two different groups, three different groups, then it's going to start, it could be polar. This is going to be nonpolar because hydrogen and carbon, that bond is nonpolar, and it's a tetrahedral molecule that's very symmetrical. So this is, all the bonds cancel out. This is nonpolar. Okay, the next one, we would draw the Lewis structure for ammonia, NH3. We have a lone pair at the top, and then we have our 3 hydrogens around. This, because we have nitrogen in the middle, we have 3 bonds in a lone pair. So that's 4 electron groups, but one is different. And then all of these electrons from hydrogen are going to be pulled towards the nitrogen. And this is kind of tetrahedral, but we have an electron group that's a lone pair on the top. So this is trigonal pyramidal. So this is going to be polar because our electrons are being pulled towards the top of this nitrogen. And sometimes it's helpful to see this 3D structure. So you can go to, I think, control click. We can get to this PhET simulation. We can practice this. So if we go to real molecules, oh, let's see. I think you can get in there. Might take a minute to load. If we look through these, we can model what it looks like in a molecule to be polar. And sometimes seeing the 3D structure helps. This is a really challenging topic, so I would make sure that I practice this a lot in the ALEX before our chapter 4 test.